Rodman Linn is the Associate Director for Fire Science of the WiFIRE Lab at the San Diego Supercomputer Center at UC San Diego and a Senior Scientist at Los Alamos National Laboratory. For more than 2 decades, he served as Principal Investigator for FIRETEC, a process-based coupled fire atmosphere model. He leads the Los Alamos Laboratory efforts to use next-generation process-based wildland fire models for the study of fundamental fire behavior and evaluation of prescribed fire tactics.
Hi, I'm Rodman Linn. I'm a senior scientist at Los Alamos National Laboratory, and I'm going to talk to you a little bit about some of the modeling work that many of my colleagues have been working on. Namely, I'm going to talk about next generation wildland fire modeling and the opportunities and challenges that it poses. In order to set the context for this presentation, I'd like to make the point that wildland fire and what we think of as fire behavior is the result of many interacting processes. Some of these processes include moisture evaporation, combustion, heat transfer, or fundamental fluid dynamics. Many of these fundamental building blocks are understood to some extent and have been studied for other applications. However, when they work together, they combine a dynamical system that's very complex and has many feedbacks. And that's what we usually think as wildland fire behavior. Wildland fires, which includes wildfires and prescribed fires, are not all the same. Intense fires, which are what we oftentimes see in the news, for example, have strong drivers, that is, strong winds, dense or continuous or extremely dry fuels, steep slopes. And these factors are often at landscape scales in order to keep that intensity going for extended periods of time. The strong drivers make these fires relatively resilient to fine-scale heterogeneities in fuels or short-term wind lulls and gusts. This actually increases the predictability of these fires. Low-intensity fires, on the other hand, which can include backing, flanking, or even prescribed fires, typically lack these strong drivers. They can be low wind speeds, or moderate slopes, or moderate moisture conditions, for instance. And the susceptibility or ability for these fires to escalate depends on localized conditions. This means that a fire might accelerate just because it moves out of fuels that were in the shade into areas that were in the sun predominantly for the morning. This dependence on local or fine-scale conditions makes these fires more difficult to predict, as the correlations between transient or fine-scale heterogeneities really matters in their predictions. There's a full spectrum of models available these days, ranging from graph-based, one-dimensional fire spread models out to computational fluid dynamics models that couple the fire and the atmosphere. When we choose between these different kinds of models, it's important to realize that there's a lot of compromises that occur and trade-offs between these models. Some models can do larger domains and have smaller computational costs. Some models can provide greater detail or versatility. Run times can be a consideration. The availability of computational power should be a consideration. And the detail available in the input streams should be considered when choosing between these models. Another way to think about wildland fire models is to consider the application space for which they're intended. This is another way of saying this is what uses are they planned for? We have some models, as illustrated on this conceptual graph, that are intended to run very fast and provide estimates of fire behavior at rapid pace to support real-time decision making, such as happens during a wildfire event. On the other hand, we have other applications that are more for planning and thinking ahead. These types of applications typically don't have as much of a time requirement, but they may have a much stronger need for details, and their inputs might be much more complicated. But luckily, they can run for longer and don't have to be done quite as fast. Many of these applications that can be run for longer periods of time and require much more detail are designed for proactive solutions. The minute we start doing things like planning prescribed fires or doing fuel treatment optimization or thinking longer term about wildland fires and their feedbacks with ecosystems or watersheds, we need to be thinking very detailed and thinking about all of the different connectivity between the wildland fire behavior and things like fuel structure. Vegetation is a critical input for most wildland fire models. Nearly all fire behavior models require some basic information. How much combustible biomass is there? How is it distributed? What is the moisture content of that fuel? And the nature of the fine fuel particles. It's things like surface area per unit volume. For the application of fire behavior models to many fire scenarios that are emerging in that proactive category that was discussed earlier, it's important to capture the three-dimensional structure of the vegetation and the distribution of properties within that three-dimensional matrix. This allows us to capture fire sensitivity to geographic or ecosystem gradients, such as moisture gradients that change with elevation. It also allows us to capture things like the evolving mixture of different vegetation types as a function of space. By capturing the three-dimensional structure of the vegetation, we're also allowing for the inclusion of the effects of treatments. And those treatments might not be clear-cutting. They might just be taking out a few trees, for instance, or prescribed fire, which removes some of the understory and partially the mid-story. It allows for the capturing of the influences of natural disturbances as well as climate-induced changes, say some mortality of some of the vegetation throughout the landscape. If we imagine flying over these landscapes in an airplane, we might look down and perceive that the vegetation is homogeneous over some distance. However, if we take a different perspective in the context of low-intensity fire, these same landscapes might be very heterogeneous because the heterogeneity is tied to the scales associated with particular fire activity. As mentioned earlier, low-intensity fires can be significantly affected by small gaps or small patches of extremely dry fuel. So the heterogeneity of the system is tied to the fire activity that might be present on that landscape. One approach to developing these next generation wildfire models, especially those that are intended for the more proactive application spaces, is the use of computational fluid dynamics. With this methodology, the fundamental building blocks of fire behavior can be coupled with three-dimensional vegetation structure and capturing the feedbacks between the buoyancy-driven atmospheric flows and the fire behavior itself. However, achieving adequate phenomenological representation of these basic building blocks is oftentimes very computationally expensive. Since the computational expense of some of those fluid dynamics approaches can be prohibitive for some applications, it's led researchers to start to think about new ways to capture critical fire phenomenology to support decisions in the field, especially for some of those more proactive and detail-oriented applications that we spoke of earlier. One thing that's come out of the detailed research as well as laboratory and field observations is an understanding of the critical nature of coupled fire-atmosphere interactions, the three-dimensional fuel structure, and if we're talking about prescribed fire, of course, the dynamic and heterogeneous ignition patterns that practitioners use to engineer the fire behavior that they desire. But if we're going to capture those details, it would also be nice to be able to run on a laptop or desktop computer to perform simulations in a practical amount of time, or to perform large ensembles of simulations to predict the sensitivity of fire behavior to both environmental conditions and ignition patterns. One such tool that has been designed with this purpose in mind is QuickFire. QuickFire was intended to be a fast-running tool that captured these basic critical elements of coupled fire-atmosphere interaction, the three-dimensional fuel structure, and the ability to do dynamic ignition patterns. By focusing on the coupling between the fire and the atmosphere, models such as QuickFire are able to capture the general spread and behavior of fires, even if there are multiple fire lines that are interacting. A few final thoughts on these next generation fire models. The utility of these tools depends on researchers and practitioners collaborating together. The experience-based knowledge of the practitioners is critical for vetting, evaluating, and gaining confidence in the tools, while the operational needs should drive the packaging and refinement of these models. These models are oftentimes never done, so their continued evolution depends on that feedback between practitioners and researchers. Researchers often don't know what information is most critical to support decisions, and so the guidance is absolutely essential. And finally, models designed to support many proactive wildland fire management applications are quite different from existing operational wildfire spread models.